for inviting me here in this wonderful colloquium. I'm really looking forward to hear all the other talks. So good morning, everybody. I will talk about the microstructure evolution during laser powder bed fusion. And so this is quite a big effort of many people, and I will start off by acknowledging them. If I can go to the next slides. Okay, it's better. So all the work that we have been doing is performed in the group of Helena van Zwekenhoven at the Scherrer Institute. Sami Hossein was a PhD student at the time in our group, has built the device that I will show you later and also performed the experiments. And then we also had the help of Cynthia and Turdi for doing the beam times and also electron microscopy measurements. I will also show you some radiography experiments that we have performed, and that was done in collaboration with Roland Logé, with Charlotte de Formanoir, Hossein Kassemi Tabazi and Navid Sorabi. All the experiments that I will show you were done at the Swiss light source, and so this cannot be done without the help from the BIMA scientists, and I particularly mention here Daniel Krolemund, Darro Sanchez, Nicola Cassati, and Federica Marone from the 3 different beamlines where we have done the experiments. And we have also used an in-house built detector without which these experiments would not be possible. So I would also like to acknowledge Gemma Tinti and Erik Freud for that. So I will be talking about laser powder bed fusion. So everybody knows the principle, I guess. We deposit a thin layer of powder, and then with a focused high power laser, we locally melt our material. We get very fast solidification locally where the material was molten. And in this way, if we do this layer by layer, we can build our 3D object. Now this process is quite a violent process, quite a complex process, as shown here in this schematic. Now everything that happens here at the top above our powder bed, this can easily be monitored, or it can be monitored with using process monitoring sensors like fast optical cameras, thermal cameras, photodiodes, parameters, and so on. And these are typically available in commercial devices. But we are interested in what is happening here at the bottom, below in our powder bed. We want to know how the microstructure is evolving while we are printing. And so this we can do by X-ray diffraction, and this is what I will show you today. But there's also other methods like acoustic emission, or one can use thermocouples or strain gauges to follow what is happening inside our material. Now, using X-ray diffraction has been done before. I show you here a few examples where people have used high energy X-rays to investigate the interaction between a high power laser and powder. And so typically what has been done is that the powder is being confined between two plates, typically with a distance of a few hundred micrometer. And then with high energy X-rays, we shoot in transmission through the sample and then use imaging or diffraction to investigate what is happening in the sample. Now, of course, this is 2-dimensional, and this can have some artifacts that really do not represent what is happening in a 3-dimensional case. So therefore, we decided a few years ago to actually build a true 3D printer that mimics really what is happening in commercial devices. And so this brings me then to the overview of the presentation. So I will show you first this device that we have built. I will show a few details about that. And then I will show its functionality in 2 different parts. In the first part, I will talk about how we use X-ray diffraction to look at the phase and temperature evolution in TIE 6.4, and also how we use this then to evaluate some heat source models that are used in simulations. And in the second part, I will also shortly talk about how we can use radiography to observe cracking in nickel superalloys. So I will start off now with the device itself that we have built a few years ago. So this was built by Sami Hossein, shown here on the right top. And so the first thing that we notice about this device are its dimensions. You can see it's fairly small. only 50 centimeter high, and so this can be easily transported at different synchrotrons and installed at different beamlines where space sometimes is restricted. We see here at the top a scanning unit. So this is a 2-mirror system, commercial one, that put the laser beam that comes in from the side through this objective and then into our printing chamber. You also notice here an X-ray exit window where the X-ray beam that can come in from the back can exit in the front. And the whole thing is mounted on a tilting stage, and we will see later why this is important. When we open it up, then it looks like this here. So I'll show you a few important components. We have here in the back the X-ray entry window, which is made out of glassy carbon. We have here our recoater system. So this is a little funnel that we can fill up with powder, and this one can move over our powder bed, over our build plate here, and this one can be lowered like in a regular device. What is also important is that here we have inlets for inert gas, so we can do the measurements in argon or helium or nitrogen atmosphere. And so with this device, we can just print samples using the usual scanning strategies, so unidirectional, bidirectional cross-hatch, and so on. So we will be using mainly the bidirectional case here for these for the experiments that I will show you, both in diffraction and in radiography mode. And so with this printer, we can print full 3D objects, like in a commercial device. So for our in situ or operando experiments, we typically print quite simple geometries, as shown here, so simple cuboids. But to show you that we can also print more complex objects, I show you here a 3D rendering from the Matterhorn mountain in Switzerland, and then we can slice this up and we can also print that as is shown here on the right. So this is made out of bronze, and this 3D Matterhorn. So this is a device that can print full 3D objects just similar as a commercial 3D printer. But we can now put it into a synchrotron beam and do all kinds of exciting experiments with it. So we start off with the diffraction mode. And this is shown here, a schematic of it. So we have our X-ray beam, which is focused down to a few tens of micrometer. It goes to the back of our machine onto the powder bed. And so here you can see why we have to tilt our machine. Otherwise, we do not have access to the powder bed with our X-ray beam, because the X-ray beam obviously is parallel at a synchrotron. We can tilt the machine typically up to about 20 degrees. Up to those angles, the powder remains always very stable. After the interaction of the X-ray beam with our material, it diffracts. And then we have the diffraction signal being recorded with a detector which is placed just simply behind our device. And so we see here from the top the laser interacting with our powder bed. This is how it looks like at the beamline. So here we have some focus optics. This is at the Microstructure beamline. The beam comes from the left here. It focuses the beam onto our device, which is tilted here at 20 degrees, and then the diffracted beam is recorded with our detector that is mounted here on this arm, so we can change the height and the position and so on of this detector. Here I show you an animation of the actual process. So first we lower our build plate by 30-40 microns, and then with the recoater we deposit a layer of powder, and then we position our X-ray beam at a fixed position. This is super important. We do not move our X-ray beam, we only move our laser. So the laser is scanning. So this means that at the beginning our laser is far away from our sample. We get closer and closer. We start to see the heat of this laser, and then at the end the laser is moving further and further away, and at some point it's too far away to see any changes anymore in our diffraction pattern. And so this whole process typically takes about 1 second. So I will show you now a case study, this TI64, and see what we can learn from this method. So we know that pure titanium has two phases, alpha at the low temperature and beta at the high temperature. But now if we add aluminium and vanadium to obtain the well-known TI64 composition, we can make this into an alpha-beta material. So what happens if we are heating up our material, we get into the high temperature beta phase, which is a cubic phase. And then when we cool down, we in principle can obtain the alpha and the beta phase simultaneously. So the alpha phase is an HCP phase. So in a diffraction pattern, we can very easily distinguish between those two phases. Now, if the cooling happens very fast, then we can actually suppress the formation of the beta phase. And this is happening, of course, during laser powder bed fusion, where the cooling rates are super high. And so what happens there is that we obtain a martensitic transformation, and we end up with a microstructure as shown here on the right, a typical needle-like structure for the alpha prime phase. Now what we see is that the alpha prime phase and the alpha phase have very similar lattice parameters. So in a diffraction pattern, they're not so easy to separate. In high resolution X-ray diffraction we can, but in our case we will see that the diffraction patterns do not have sufficient quality to really separate those two phases. So when I talk about the alpha phase, I'm actually meaning alpha and alpha prime phase simultaneously. So here I'll show you the powder. We have the nice spherical particle shape, which is very important for good powder flow in our sample, in our powder beds. The particle size distribution is a typical one, 20 to about 60, 70 micrometer. And here we did some X-ray diffraction before printing and did a refinement of that, and we find that we have about 60–40% alpha prime phase in this material. So we do not have beta phase to start with. Here I now show you an example of, or a schematic or an animation of the actual process. So here at the right bottom, I show you the interaction of our X-ray beam with our sample and the diffracted beam here. I then show you here at the right top a single diffraction pattern as a function of time, and we will see how this is changing when the laser is moving back and forth on our sample. And on the left here, I show you a stack of the different diffraction patterns as a function of time. So we start off with purely the alpha phase as seen here, and from the moment the laser starts scanning over our sample, we see at some point, you will see that here at the right top, we create the beta phase, and then the sample cools down and we go back to the alpha phase. And this happens multiple times. So if we now look at this stacked plot here, you can see how our alpha phase is then going to the beta phase here. This is this little comma here, and then we go back to the alpha phase, back to the beta, and so forth. And so we do this multiple times. And this typically takes about 1 second to complete the whole process. So what can we learn now from this kind of experiments? So we can obviously look at the peak intensities, which will tell us something about this phase transformation between the alpha and the beta phase. Not important here, but in some other materials, you may also want to look at precipitation or also the evolution of texture. The other parameter we look at is the peak positions, and from the positions of the peaks, we can actually calculate an elastic lattice strain. And then, so I'll show you here, for instance, this is one of those commas, one of those betas, evolution as a function of time. We can track the position of it, and then we can calculate it into a lattice strain. And then using the thermal expansion coefficients, we can then get a measure for the temperature that has caused this, this kind of lattice strain here. And so I will show you several temperature curves in what follows. So now that we have this, we can vary a lot of different parameters. So we have been playing around with the power, with the scanning speed, hedge distance. But what I will focus on today is the influence of the scan factor. The idea behind this is that when we are printing a sample, we can print it with small or large scan factors. This can be, for instance, because of island scanning, or when we really want to print very small structures, open cell structures, for instance, the scan factor can be quite small. And so what we have done is many operando experiments on samples with various sizes. And I will focus on two different sizes, one where we have a scan vector of 8 millimeter, so we go back and forth over 8 millimeter in length, and we're going to compare that with another sample which is only 2 millimeter in size. And intuitively we already know, of course, there's going to be an influence on the thermal history, and with our method I will show you that we can actually track this and quantify this difference. And so all the other parameters will be fixed. So the only thing we vary is the scan vector length. So these are those parameters. So we start off with a laser spot size of 100 microns. We can vary it down to 25 microns. That's the minimum spot size available to us. A power of 250 watts, we can go up to 500 with our current system. And we use a scanning speed of 600 millimeter per second. So you see these are typical parameters used in conventional printers. As I said, we have a bidirectional scanning strategy. The layer thickness is 30 microns and there's no preheating of the sample. For the diffraction parameters, we use an X-ray beam of 12 keV, which is relatively low energy. So we will be looking mainly at what is happening in the very first layer. So we do not penetrate deeper than one layer in the material. We have a spot size of about 80 times 140 microns. And the X-rays are detected with an Ecole detector. It's a 500,000 pixel detector, which is operated at 20 kilohertz. We can go up to 40 kilohertz. Now, of course, at this very high speeds, we cannot have a very high dynamic range. So it's limited to a 4-bit dynamic range for these kind of measurements. But this is more than sufficient for these kind of applications. So here I show you again now this waterfall plots, as I shown you in the beginning in this animation. And we can already see by looking at those that we have a big difference between our 8 millimeter scan vector and our 2 millimeter scan vector. So when we look at the 8 millimeter one on the left, we see as before, we start off with purely the alpha phase. Once our laser is approaching the area that we probe with our X-ray, we see that our sample is slowly heating up, or the probed area is slowly heating up, and at some point the temperature is high enough that we start seeing the beta phase. So we see the peaks moving to the left because of thermal expansion, and then we see new peaks popping up of the beta phase. And in this case we see the 011 beta phase here and the 002 beta phase also here on the right. And so we see how we go back and forth between the alpha and the beta phase. At some point the laser beam is far away and then the sample slowly cools down, and so our peaks slowly move to the right because of thermal contraction. If we look at our 2 millimeter sample, it's very different. We also see how the alpha is heating up, but once we have created a beta, we simply stay in this beta phase for a long time, a very extended period of time, and at some point again our laser beam is far away and we create alpha phase again. So let's have a look in a bit more detail what is happening here. First, the 8 millimeter sample. And I'll show you here the evolution of the intensities of the beta phase at the top, the alpha phase at the bottom, and then also the temperature. So this is, again, we see here the temperature in the alpha phase, which is shown here at the bottom. When the laser starts scanning our sample, we see the heating up, slowly heating up. There's a bit of variations in this intensity because there's particles flying around that are interacting with our X-ray beam. And then at some point, and this is shown schematically here at the bottom, our X-ray beam, which is shown here in yellow, is overlapping with our laser. Just so the laser is on a track that is very close to our probed area, and the temperature becomes high enough to actually create a tiny bit of beta, but there's very little overlap. And we see how our alpha phase then at some point starts to decrease a bit. And so when we do the next track and the next and the next, we get more and more overlap with our probed area, and we see more and more of this beta phase. And in line number 17 in this particular case, we get the most overlap between both. And here you can see how the temperature in the beta phase is evolving. So what I will do now is I will show you in a bit more detail what is happening on this line number 17. So that's shown here. There's a lot of data on this plot. Let me walk you through it. So let's first focus on the blue and the red curve here. So we start off with the alpha phase. That's the intensity of the alpha phase, the blue curve. And we are in a situation, as shown here on the right, where our laser beam is approaching our probed area. When we are hitting, when the melt pool is actually overlapping with our probed area, a lot of the intensity from our diffraction peaks is distributed in the areas between the diffraction peaks, the so-called diffuse scattering. And this is shown here with this gray curve. And so by looking at this diffuse scattering, we actually have a very good timestamp of when the laser beam hits our probed area, and this with an accuracy of about 50 to 100 microseconds. So at that point, we get the formation of the beta phase, which is shown here in the red curve, and our alpha phase is disappearing. So at this point number 2, the laser beam has already passed our probed area, and what we see now is the cooling down of our sample. So this is shown here. This is the yellow curve, is the temperature in the beta phase. We can see how it cools down slowly, and at some point the temperature is low enough that the alpha phase is created again, and then we can follow the temperature in the alpha phase. And so at some point the laser turns around, comes back, and at this point number 3, we are ready for the next interaction between the laser and our X-ray beam. And so this is repeating over and over again for the different tracks. Life is very different for the 2 mm sample, where we have the following situation. So we start off again here with our printing at this point, the dotted line. We see at the bottom here the temperature as a function of time. We see how the temperature in the alpha phase is increasing. At some point, temperature is high enough that we start to have the creation of the beta phase. We see how the alpha phase is decreasing at the expense of the beta, or the beta phase is increasing at the expense of the alpha phase. And at some point, the alpha phase is completely gone, and we only have the beta phase left. And so we see here also on this schematic here that at this point number D, the laser is already several tracks away from our probed area, but the temperature remains high enough because of the short scanning factor length to keep this beta phase for an extended period. And once the laser beam is really far away, the temperature, as you can see here, is slowly cooling down with typically rates of about a few 10,000 Kelvin per second. If temperature low enough so that we create the alpha phase again and our beta phase is disappearing. You may wonder what is happening here with these temperatures. So this is because when the alpha phase is growing inside the beta grains, there's a difference in lattice volume or unit cell volume, and this creates locally some stresses in the material. So we get this artificial change in the temperature curve. So what can we learn now from this? Well, what we have shown with these experiments is that if we change the scan vector length from 8 mm to 2 mm, our beta events have a very different lifetime. In the 8 mm, they typically last for about 7 milliseconds or less, whereas for the 2 mm scan vector length, we have beta phase during 84 milliseconds. And so you can, of course, imagine that this will have a big influence on our final microstructure. So this we have investigated by using EBSD. We have done that on a sample of 2 mm and 6 mm, but the 6 is very similar to the 8 mm in terms of its response. And I'll show you here then the typical microstructures that we get for the alpha and alpha prime microstructure, typical needle structure. So you immediately already see here a very clear difference in the microstructure. Now there's a orientation relationship between the alpha and the prior beta grains where they have grown in, and so based on this orientation relationship, we can actually calculate back the shape of the original beta grains, and this is shown here. So now it's even more visible what the influence is of the length of the scan vector. In the case of the 2 mm sample, because we are such a long time at this elevated temperature, the beta grains have grown significantly larger compared to our 6 mm sample. So based on this, we just simply looked at the events, at the length of our beta events, and we could make some conclusion about our microstructure. But of course, we have the full temperature curves. And this allows us now to actually look at simulations and see how well these simulations can reproduce our experimental results. And so what we have done is we did some abacus simulations, finite element simulations, and we have looked at various heat source models. So I should very quickly talk about that. I'm not going into details. So here is the model itself. So we just simply distinguish between the powder and the bulk. And in the bulk, we distinguish them between a build plate and a sample. We have different meshing sizes there and different boundary conditions. And so we have then different parameters used for the powder and for the bulk, the usual ones as can be found in literature. And then we have used different heat source models. So basically those models represent the interaction of the laser beam with our material. And so for TI64, there's we found these following three models from the literature. So one of the main differences is the geometry of these sources, of the heat sources, and whether or not radiation losses are taken into account. So in one case, it's an ellipsoidal model, or we have a double ellipsoid model, as is shown here, to mimic the tail that you have in such a melt pool. Or there's also cylindrical and parabolic model here. In this case, the radiation losses were ignored, so we then added also the radiation losses ourselves. So we have basically end up with 4 different models where we then try to follow the temperature evolution as a function of time. So I just show you here an example of such a simulation. So we probe here with our X-rays at this point here. And so in order to mimic what we do in the experiment, we take away the liquid part, because the liquid part we cannot measure with our X-rays. And then we actually average the temperature using the same shape as the X-ray beam that we have used in the experiment. So we do a weighted average of the temperature on the different nodes around in this X-ray probed area. And so from that, we end up with temperature curves as function of time for the simulations, and this we can compare with our models. So I show you here on the left again such a waterfall plot, but now turned 90 degrees. So we have the diffraction angle as function of time here. So we start with the alpha phase, go to the beta phase, and then go back to the alpha phase for the 2 millimeter sample. And so this results here in these 2 solid curves. So the purple one and the pinkish curve is the alpha and the beta temperature evolution. And then the dotted line shows the temperature evolution for these 4 different models that we have been looking at. And when we look in a bit more detail, we can see how the different models are performing. So obviously, some of the models, they strongly underestimate the temperature. Other ones have too high cooling rates and so on. So with this method, we can actually really look how well these models are performing, or we can then also look at how the melt pools are, how they compare with our results, also with microscopy results, and so on and so forth. I will not go into the details here, but you can read all about that in this paper here in additive manufacturing from Sami. So for the last 10 minutes of the presentation, I will switch now to radiography mode. With our diffraction, we have the possibility to look at evolution of the phases and the temperature and so on, but we can't see defect creation. And in particularly, we are interested in looking at the evolution of cracking and pore formation and so on in our samples. And of course, radiography is there the established method. So this is the setup. So again, we tilt our machine by 20 degrees. But this time we do not have a focused X-ray beam, we have a parallel X-ray beam that is illuminating big part of our powder beds, and then we work in transmission mode. So this is shown here at the right bottom. The beam comes here from the right and then interacts with our sample here at this corner, and then is detected by our X-ray detector. This is the relatively simple radiography setup. This is how it looks like at the beamline. So the beam comes here from the left. This is again our machine is tilted. And then here is the microscope with the 4 times magnification. And at the top you see our detector. So how do we have to interpret the results of these experiments? It's not so straightforward because we are working in radiography mode, not in tomography mode. We get a projection of our samples. So we are looking at basically a wedge like this. This is our sample. The beam goes here back and forth, and we are projecting everything along the beam path onto the detector. And so if we have a crack that, for instance, runs like this, perpendicular to the surface, we will then see it. In this case, the crack will go vertically here, but it will not come completely to the top because the top is actually representing the edge of the sample here. So that is something to keep in mind. We will also see pore formation, and we can also in principle look at powder ejection or spatters that are created, but we will not concentrate on that. So we have used this technique on a nickel superalloy. And this was had a size distribution of 15 to 45 micrometer. And here we can see the chemical composition of it. Here are the beamline parameters. So we work with a wide beam because we really need a lot of photons to do these experiments at high speeds. So we had a beam with energies from 10 to 55 keV. The detector is also a PSI built detector. It's called gigafrost. And this allowed us to work with the frequency of 10 kilohertz, but now in 16-bit mode instead of 4-bit mode. So as said, we had a 4-time magnification, so we end up with an effective pixel size of 2.75 micrometers. So it's not super high resolution, but it's good enough for what we want to do, as you will see. And the field of view is fairly large, so that we can try to see as many cracking and other events as possible. The printing characteristics, so again, we work with a 100 micrometer beam. We had 160 watts power and scanning speed of 220 millimeter per second, so a bit slower, but still relatively fast. And again, we work in bidirectional scanning strategies. The base plate is 316L, but before we actually do the experiment, we first build quite a bit of material. And so with this material is not so relevant. There's no preheating, and layer thickness was 40 micrometer. So I will show you a few radiographs as function of time, and I want you to focus here on this area. The laser beam will come here from the left, and you will see a bit of the melt pool, so a shadow of the melt pool here that is going from left to right, and then a crack will be created here in the middle of the sample when the laser beam is already further away. So here is this melt pool moving, and you can see the formation of the crack here, which was not there before. Now you may wonder, a crack should be less material, so why does it have a dark contrast? Why is it black here? And we were wondering ourselves. And so the point is that these cracks are very narrow. And as I said, we have this 2.75 micrometer pixel size, and they're actually relatively difficult to observe without doing edge enhancement. So that's why our detector was actually put quite far away from our sample, so that we get this so-called edge enhancement effect. We have done 3D tomography afterwards on these samples, and I'll show you just here a cut through this to such a tomogram, where we can see how pores and cracks now have the same kind of contrast as you would expect. So here we do not have this edge enhancement because we were working in high resolution mode. So we are absolutely convinced that what we are seeing are actually cracks. The other thing that we can see are pores. So I'll show you here another graph, and so the laser beam will first come from the right. We will get the creation of some pores, and then the laser beam will go there, come back and create some more pores, as you can see. So here we see this pore formation. The laser beam goes now to the left side. Now it's coming back. It's here, and we can see the creation of some more pores. The other thing we can see is actually the removal of those pores. So we can see the laser beam coming here from the right, and then some of these pores will actually be removed. So these are the typical things that we can observe in this radiography experiments. So let's look at a bit more at some of these things in a bit more detail. And we're going to focus on the cracking mechanism. I want you to focus here on this area A. So at T0, our laser beam is just passing this region A here. And so there was nothing there before the laser beam was hitting it. And then when the laser moves further, a crack starts to appear at about 2 to 3 milliseconds after this laser beam has passed this area, and the crack is completed basically at about 4 milliseconds after the laser beam has passed this area. Then the laser beam turns around, comes back, and then there is a remelt, there is a melting of this top part, and so part of the crack is actually remelted, and then at some point the laser beam is far away again and the crack reappears. And so this is a scenario that is coming back, that we have seen multiple times in various samples. Another mechanism that we have seen is shown here. Here we have a crack that is already present from other previous tracks or so. And then we see how when the laser beam is passing, there is no interaction between this cracking and the laser beam. So this crack remains just stable when the laser is passing by. But when the laser is a bit further away, then we see how this crack is growing. When the laser is then turning around and it's coming back over this crack, then there is an interaction with this crack. It remelted, and once the laser is gone, the crack is growing back again. So we see these two different kind of mechanisms in this material. So the question now, what is causing this? Now, when we look at after printing at the microstructure, what we notice is that these cracks, they follow basically the boundaries of in the material. And also important is that we see with EDX measurements, we see segregation of this tantalum and hafnium here around the cracks. So we can clearly see an enhanced concentration there. And so this is known that this segregation can actually change the temperature, the solidus temperature of this material by many hundreds of degrees. So the question is now, but what is then the temperature at that point when this cracking occurs? So in order to do that, to know this, we've done some simulations. So the group of Professor Logé has done this. And so I'll show you here some results of that. So we were going to look at the temperature profile at point A and point B during a simulation of the printing process. And so here at the bottom, we see the temperature as function of time. So at point A, we melt the material, it goes really high in temperature. And when we cool down to near basically room temperature, and the second track of the temperature is lower, and so forth. Deeper into the material where our cracks are actually formed, we see that our temperature does not rise above the melting point here, in this case, above 1250 C. Now, because of the segregation, microsegregation, it was shown in literature that you can actually change the solidus down by about 400 degrees Celsius. And then we can see that at this point B, we actually do rise above this melting point. So we are locally, we can actually liquefy our material. And what we also notice is that the time between our laser passing and the time that it solidifies this part again is about 2.65 milliseconds. And that is exactly the time when we see the cracking appearing. So the idea now is that because of the local microsegregation, you create a liquid by the laser passing at another track, so we're not melting the material locally, but because of the microsegregation, we are melting the area where we get the segregation. So typically at these boundaries, we get a small liquid film, and because there's always tensile stresses in this material, we create a crack. So we create a so-called liquefaction mechanism. So now you may ask the question, yes, but this comes from simulations. How do you know that these simulations are correct? So for that, we turn back to our X-ray diffraction experiments. So we have performed this exactly the same experiment, but then at the diffraction beamline, and we follow the temperature as a function of time. And here you can see the overlap between the experiment and the simulation. So we can only compare it from the solidus downwards, because of course with X-rays we cannot measure the temperature in the liquid, and we can see a very good agreement between our experiment and our simulation. So this means that we can trust these temperature curves, and we have quite a good proof that we have this liquefaction cracking occurring. So basically we have then, based on all these results, we see the two mechanisms. We see solidification cracking, where we have the solid rich liquid entrapment between the solid phases, and then we have the tensile stresses that creates this interfaces, but then also liquefaction cracking. Because of the microsegregation, we create local melting at these boundaries, and so together again with the tensile stresses, we create this cracking in the material. So this brings me to the end of the presentation. I hope I've shown you that X-ray, operando X-ray diffraction and also imaging are powerful tools to investigate microstructure evolution in laser powder bed fusion in conditions that mimic quite well what is happening in commercial printers. I've shown you by X-ray diffraction how we can follow in Ti 6.4 the crystallographic phases and the temperature, also cooling rates during printing. And in particular, we have shown how we can with this method, you can really understand the link between the length of the scan factor and the thermal history, and then the final microstructure of the material. Using radiography, we can see the formation of cracks and pores during printing. And so for our nickel supralloy, in this way, we could actually combine it with diffraction and simulations and also post-mortem characterization. We could show the two different cracking mechanisms present in these alloys. And so with this, I will show the acknowledgements again of everybody who collaborated on this work and also the funding agencies. And I'm happy to answer any questions you may have.
Thank you, Stephen. That was an amazing talk. The floor is open for questions, please. Yes, Aude.
Yeah, I'm opening the floor here, but I had a question. Well, first, very, very nice talk, really impressive work. I had seen some of it a couple of years ago presented by Helena, but I think this has really grown since, and it's really nice. I was wondering if the time of appearance of the crack is that precise due to the resolution, the I think 2.75 micron resolution, or you think you might delay the crack appearance because of the resolution and yeah, really short in time?
Mm-hmm. Yes, yeah, that's a good point. So the resolution is definitely not. I would say it's not the time resolution of the measurement. So we measure at 10 kilohertz. Right, so we would have a theoretical time resolution of 0.1 millisecond, but I'm definitely sure that we cannot say with 0.1 millisecond accuracy that the crack is appearing. But we can say that it's definitely not 4 milliseconds and it's definitely not 1 millisecond. So it is indeed in the range between 2 and 3 milliseconds. Right, and so if we look at our temperature range at that point, it's clear that we are exactly in the good region where we expect then this kind of cracking to occur. Yes, but it's definitely not 0.1 milliseconds. Mm-hmm. And I'm sure, indeed, you're right that it would be better if we would be able to do the experiment with a higher spatial resolution. So if we were to work with a monochromatic beam, with a high intensity monochromatic beam, life would be a lot easier. So I can imagine that this would be improved if we work at, let's for instance say the APS, where we would have higher flux, and there we could use monochromatic beam with a fast detector, and there it would be easier to see. Yeah.
Thanks a lot. Great job.
Thanks.
Eric?
Yeah, thanks a lot for the presentation. I really appreciate it. I think this is a really wonderful machine that you have there. I actually have a bunch of questions, but maybe just a single one here. So you said that you think this is a liquefaction type of mechanism. And I would say this is, well, what I have seen from the presentation is a combination. So first you have a crack and then it remelts and extends. So I would say it's probably first there's a crack and then you have this liquefaction. Or do you also think that the cracks initially form by liquefaction? So in other words, you have sort of perfect solidification, no crack, and then only the remelting triggers the cracking.
Right. So basically, we for sure have also this liquation cracking because we have the formation of cracks before our X-ray or the laser beam is hitting exactly where the crack is. So we have the formation of cracks caused by the heat effective zone found from the laser. So without actually melting that area where the crack is formed.
So sorry, I didn't get that. Is the area where the crack formed then already bulk, or is that still powder, or how
No,
does that work?
well, it's definitely bulk. So it's definitely bulk, right? And so what we see is the formation of these cracks also when the laser is not exactly above the crack. Mm-hmm. So we are definitely not melting globally. I mean, as a proper melt pool where the crack then later appears. So we also have that, but we then have also the cracking appearing without that the laser really was over the point where the crack occurs. And so this means that it's really just local heating, or let's say the heat is high enough to create this local cracks.
Local melting, yeah.
Local melting.
Can you actually detect the edge of the melt pool? I mean, I've seen this in the papers from Tony Rollett's group, right, that in some materials they can really detect the edge of the melt pool, and there it really looks like. I mean, yeah, and with nickel it's not so easy, but sometimes you can really see sort of the, where the solid liquid interface is moving. This is where the crack is starting. So that sounds and looks very much like solidification cracking, right? Yes,
exactly. So here it's indeed a bit more tricky because we are working with this white beam, and so our contrast is not super high. So once we go to monochromatic beam as they have done, and they can also measure super fast in their setup, you can much better investigate the melt pool itself. So we do not have the optimized setup for doing that, not at this beamline. We would have to go to another beamline to do that. And then we should be able to do the same thing, indeed.
Thank you.
One last question from Charles-André, and then we move on to the next talk.
Yes, thank you, Manas. Well, wonderful presentation. Thanks a lot. I was very much fascinated by the results about cracks. So, of course, with EBSD, you see that the cracks are mainly intergranular, and this is typical in these alloys. So, my first point would be, could you try a single crystal experiment? There are two reasons for, or big crystals maybe, with a controlled orientation of the two single crystals that you have into contacts. There are several reasons for that, of course, because it's mainly intergranular. It would be nice to see the effect of the grain misorientation of your big crystal, to see the propagation of the cracks, whether or not it happens, and what is the influence of the orientation of the grains. And the second reason is that you might want to improve the spatial resolution of your images by using topography instead of radiography. So if you have a magnification in the diffraction spot in the topography analysis, you directly see the grain and its topology at the boundary. And that definitively will, I think, will improve your resolution, spatial resolution.
Yeah, well, for your second part, that's an interesting idea. I do have a bit of experience with X-ray topography, and from what I learned is that the intensities will be too low to do these super fast measurements in topography mode, I think. So that will be that would be quite tricky to actually look at the diffraction inside the diffraction spot. And you also need, of course, quite high resolution detectors for that. But it's an interesting idea, indeed.
Well, with respect to that, I mean, there is a team doing solidification studies in Marseille where they use it regularly. And so you might want to check what they do in details. If you
Okay. Thanks for the suggestion. Yeah, we will look at that.